Eigenvalues were already negative or had negative real part, and these have even more negative. Diffusion coefficients are, of course, positive, and of course, minus k squared is positive. So it's even more stable. So that's the intuition. And what Turing found was that if or explored a case in which if the two diffusion coefficients are different, are sufficiently different, then you can have instability to something like e to the I kx, where you didn't have instability without spatial variation. Okay. So no longer going to have the eigenvalues both being decreased. So we return to our famous diagram here. Remember, we presented this again in the very first class, the behavior of a 2x2 linear system, the determinant and the trace. We had, this is where you have complex eigenvalues in here, and so you have unstable spirals and stable spirals. And here you had nodes outside, stable nodes with two negative eigenvalues, unstable nodes with two positive real eigenvalues, right? And over here you had saddles with real eigenvalues, one of which was positive and one of which was negative. So the coloring is to say that, excuse me, you need, I should say, these are stable. You see that from the words, stable, stable, stable. These are unstable. The saddles are also unstable. They are unstable in one direction, stable in the other, okay? So we see from this picture that for instability, you either have to have the trace being positive or you have to have the determinant being negative. If the trace is negative and the determinant is positive, then you're stable. So you need one of these two conditions. And let's see how that works for the system of equations we just set up. Since since this homogeneous solution is stable, then the trace is negative and the determinant is positive. Is stable. Okay, and the trace, we're talking about the Jacobian, so we're talking about FU plus GV. So this has to be negative, and the determinant, well, you know, it's this times this minus this times that. So we already have this necessarily. And now what we want to see is, can we get one of those two conditions to be violated by putting in the diffusion? Well, the trace thing we can't, because the trace we can easily see. We talked about eigenvalues and simultaneously diagonalizable and commuting and so on. That might be a little complicated, but the trace you can easily see. The trace, what you add to the trace when you add this matrix is you have this, and then you have minus k squared times du minus k squared times dv. So of course that's less. If this trace was negative, well then this one's even more negative. That part, that's always true. You don't need to know anything fancy about commutation or anything. So you're not going to get your instability by violating this. The trace isn't going to become positive. Okay, so forget that. For instability, perhaps the determinant goes from being positive to negative. So then we just do the calculations. We say, if we put in the k, if we put in the spatial dependence, and we just multiply out, we go back to here, and we do this times this minus this times this. We're just looking for the determinant. This times this minus this times this. So you see that part of it is a homogeneous determinant. We have fu times gv minus fv times gu. But we also have minus du k squared gv minus dv squared k squared fu. And then we have plus du dv k to the fourth. Right? Okay. So we have all that. So we have the original determinant, which is necessarily positive since the original guy was stable. Then we have the k to the fourth term that we got from the product, and then we have the k squared term. This one's positive, and this one's positive. Right? So the only chance could be if this one is sufficiently negative as to make the determinant that used to be positive here negative. Okay, so we need this for this to be negative, and hence you see, well, no, we'll just say that. You need this for the negative. So let us take this determinant and let us find the minimum. Because certainly if the minimum, we're looking for negativity, and if the minimum is positive, well then of course everybody's positive. So let's look for the minimum. So we just differentiate this, and since it's an even function, let's differentiate with respect to k squared. So here, so we get twice du dv k squared. Here, this is the square of the square, right? And here we have minus du dv fu plus du gv, and nothing here because this is a linear function of k squared. And I've written k star here because this is the minimum. We're setting it equal to 0. And so we get a formula for k star. That is the k that yields the lowest determinant. We want that lowest determinant to be negative. So what we need, okay, we want it to be negative. Excuse me, what am I saying? No, excuse me. I mean, we do want the lowest value of the determinant to be negative, but the k squared, this has a solution. And supposing that solution for k squared is negative, then that's not a proper k squared. That's telling us that we don't, that this won't work. So we need for k squared, this solution to this minimum derivative, to be positive. This is already positive because diffusion coefficient is positive. And we need for this thing here to be positive. Okay, so that is one of the conditions that we need. And, I'm sorry, so we need for the k squared value at the minimum to be a proper k squared value. And we want the determinant to be negative at that minimum. So we plug in this solution here into this expression, and that's what we're doing in the next set of equations. Here's the determinant. Here is that special minimum k star squared. And we plug it in. Here's the expression for the determinant. And we plug in, this is the square of this. Sorry, I think that maybe I should have, this is true, let's see, squared. I'm missing, I think, something here. Is that true? I'm missing a squared. Am I missing squared here? No, I'm not. Because this here, it multiplies by du dv. Yes, okay. So this is correct as far as I know. So you just plug in this value into this expression and you get this. So indeed you could be negative if this, remember this determinant 0 is positive and we're trying to make it negative. So if this thing is sufficiently big, okay, here we've just written the determinant, the original determinant here. If this thing is sufficiently big, then we will turn it negative. And now we have the 4 conditions, and there they are. The first two conditions just say that the homogeneous state is stable. The next 2 conditions are the ones that we just derived, that is to say, that the k squared that corresponds to the minimum is positive, and that the determinant at that place is negative. So those are the conditions for a Turing bifurcation, and that is the end of section 2, Turing. Not quite, because we have to show pictures. The first Turing patterns were produced experimentally in 1990 at the University of Bordeaux and in 1992 at the University of Texas at Austin. Turing proposed this theory, but they were never actually seen. These are pictures from the Sweeney article of Turing patterns. And this uses oscillating chemical reactions. And people have proposed this as a mechanism for differentiation within embryos, formation of patterns on animal coats, zebras, leopards. Whenever you look for an article on Turing patterns, you will immediately see, let's see if this works, pictures of zebras and leopards. Let's see. Images. Turing pattern. Let's see what happens. Okay, so we see pictures, and I haven't seen a zebra yet, though. Oh, we see sand dunes. Now, just because you see a pattern doesn't mean it's a Turing pattern. That is a matter of galaxy, cells, Turing patterns. There, I knew I'd find a tiger somewhere. Right, okay. So here's a tiger, or leopard. Apparently, this is how leopard got its spots. But I believe, to the best of my knowledge, this is merely, here's some fish, this is merely a hypothesis. And there is no evidence that, or shells, that these patterns are produced by the Turing mechanism. I could be wrong. This is the Sweeney picture we just showed you, proving their existence. Yeah, the Sweeney picture. how Turing patterns work. Here's Turing. Here's pictures we've been seeing. His famous paper. It's one paper called The Chemical Basis of Morphogenesis. His first and last paper on biology and chemistry. There. Okay, so I'm going to find a tiger somewhere. Find many more. Let's see. Turing patterns on Pinterest. Let's see. We have it's the same pictures. Another spider? No, I don't want to. No tiger? Ah, here's a tiger. There. Okay. So yes, to the best of my knowledge, at least when I started, when I prepared this class, this was not known. Was in fact controversial. People who thought, oh, this fancy mathematical, it's you need your biology, you need some special chemistry, you need this. I myself, of course, have no opinion about whether the Turing patterns are. I mean, I have an opinion, which is that indeed people try to sensationalize science and make it easy and make it flashy. So it's natural for people who are working on Turing patterns to put up pictures of leopards, and it's natural for people who are seeking simple explanations, and since this is well understood, to propose that as an explanation. That doesn't mean it's not true. I don't know what's true. I don't know what's true. Everybody knows the standard problem, or maybe it's been solved by now, or maybe my understanding of it is very primitive. All your cells have just the same genes, right? So you don't even need a leopard and its spots. I mean, how do some cells decide to be heart cells? How do some cells become bone cells? How do some cells become nerve cells? It's not that the cell got such instructions, because each cell got the same instructions. So it must be some wave of something that passed over it, I guess, or it's genes that are told. I don't know. I mean, things have advanced so fast and so much that I should not say anything, because surely what I'm saying would be, if I were giving this in some developmental biology seminar, people would be laughing and saying, well, I don't know. Everybody knows it's a that was discovered 10 years ago, or 20 years ago or something. Okay, so now, so we finished now 2 of the topics. And let's see, how much longer do we have, whether I should stop here or not. I have 1, 2, 3, 4, 5. Yeah, let me continue with this this next topic, and then we'll stop. This topic is called Lyapunov functionals, and let us imagine now. Let's go back. Let's again have a particular kind of dynamical system. Du dt equals minus gradient of phi. This is a particular kind of dynamical system. Not all right-hand sides can be written as minus gradient of phi. In 1D, yes, all you have to, if 1D, this would be a function of u. This is phi of u. In 1D, you would have du dt equals du dt equals f of u. If this is a scalar, then you can just write this as, you can write f of u equals du of f of u, where f is the